It is not acceptable to have only one 6 American wire gauge neutral conductor for a 20-circuit panel. The neutral conductor carries the unbalanced current from the individual circuits, and in the event of a fault, the neutral will carry the return current. According to the National Electrical Code, NEC, and Industry Best Practices, Article 220.61 states that the neutral conductor of a feeder shall have an ampacity not less than the maximum unbalanced phase current that can be supplied by the feeder. Article 310.15b6 requires that a single neutral conductor shall be provided for each set of 3 or more ungrounded conductors. With 15 to 20 amp circuits on the panel, the potential maximum unbalanced current is significant. The amp probe reading of only 7 amps does not guarantee that a fault will not occur. Furthermore, in the event of a short circuit or ground fault, the neutral conductor will carry the return current. If the neutral conductor is undersized, it could overheat and increase the risk of an electrical fire. It is recommended to move all the neutral conductors from the original panel to the new generator backup panel. Ensure that the neutral conductor has an ampacity equal to or greater than the maximum unbalanced phase current of the feeder. The importance of properly sized and installed neutral conductors in electrical systems cannot be overstated. These conductors play a crucial role in ensuring the safe and efficient operation of circuits, and any deviations from established codes and standards can have serious consequences. In a multi-wire branch circuit or feeder, the neutral conductor serves as the return path for current from the energized conductors back to the source. When the loads on each phase are perfectly balanced, the neutral conductor carries minimal current. However, in reality, loads are rarely perfectly balanced, and the neutral conductor must be capable of safely carrying the maximum unbalanced current. According to the NEC, the ampacity of the neutral conductor must be equal to or greater than the maximum unbalanced phase current. This requirement is intended to prevent the neutral conductor from overheating and potentially causing a fire. Article 220.61 provides specific guidelines for calculating the neutral load in a feeder or service. The calculation takes into account the type of loads served, the demand factors applicable to those loads, and any applicable reduction factors. For example, if the feeder serves a mix of lighting, receptacles, and motor loads, the neutral load calculation would need to consider the different demand factors associated with each type of load. The NEC also addresses the sizing of neutral conductors in specific applications, such as those serving electric ranges, dryers, and other appliances. In these cases, the neutral conductor is often permitted to be smaller than the ungrounded conductors, but it must still be sized appropriately to handle the expected neutral load. In addition to proper sizing, the installation of neutral conductors must also comply with the NEC. Article 300.3b requires that all conductors of a circuit, including the neutral, be installed together in the same raceway or cable. This requirement is intended to minimize impedance and ensure that the current is evenly distributed among the conductors. The NEC also addresses the grounding of neutral conductors. Article 250.24 requires that the neutral conductor be grounded at the service entrance or at the source of a separately derived system such as a generator. This grounding connection provides a low impedance path for fault current to return to the source, which helps to ensure the proper operation of overcurrent protective devices such as circuit breakers and fuses. In the context of a generator backup panel, the proper sizing and installation of the neutral conductor is particularly important. When the generator is supplying power to the panel, the neutral conductor must be capable of safely carrying the maximum unbalanced current from the connected loads. If the neutral conductor is undersized, it could overheat and potentially cause a fire. Moreover, if the neutral conductor is not properly grounded, it could create a shock hazard. In the scenario described, where a 6 American wire gauge neutral conductor was used for a 20-circuit panel, it is highly likely that the neutral conductor was undersized. According to NEC Table 310.16, 6 American wire gauge copper conductor with type THHN insulation has an ampacity of 55 amps when installed in a raceway or cable. However, the maximum unbalanced current from 20 amp circuits could easily exceed this value, especially if the loads on each phase are significantly different. Therefore, it would be necessary to use a larger neutral conductor to comply with the NEC. Furthermore, the fact that the amp probe reading on the neutral conductor was only 7 amps does not necessarily mean that the neutral conductor is adequately sized. The amp probe reading only indicates the current flowing through the neutral conductor at that particular moment in time. It does not account for the potential for higher unbalanced currents to occur under different load conditions. The NEC requires that the neutral conductor be sized based on the maximum potential unbalanced current, not the actual current flowing through the conductor at any given time. In addition to the sizing of the neutral conductor, it is also important to ensure that all of the neutral conductors from the original panel are moved to the new generator backup panel. This is necessary to maintain the integrity of the grounding system and to prevent the flow of neutral current through unintended paths. When multiple neutral conductors are connected to the same grounding electrode, it can create a condition known as circulating neutral current. Circulating neutral current can cause a variety of problems, including increased energy consumption, equipment overheating, and nuisance tripping of circuit breakers. Therefore, it is essential to ensure that all neutral conductors are properly connected to the grounding system and that there are no unintended paths for neutral current to flow. In summary, the proper sizing and installation of neutral conductors is crucial for the safe and efficient operation of electrical systems. The NEC provides detailed guidelines for sizing and installing neutral conductors, and it is essential to comply with these guidelines to prevent the risk of fire, shock, and other hazards. In the case of a generator backup panel, it is particularly important to ensure that the neutral conductor is adequately sized to handle the maximum unbalanced current and that all of the neutral conductors from the original panel are moved to the new panel. Ignoring these requirements can have serious consequences and could put lives and property at risk. Firstly, the NEC requires that the neutral conductor be sized based on the maximum potential unbalanced current, not the actual current flowing through the conductor at any given time. Secondly, the amp probe reading only indicates the current flowing through the neutral conductor at that particular moment in time. Thirdly, it does not account for the potential for higher unbalanced currents to occur under different load conditions. Fourthly, moving all of the neutral conductors from the original panel to the new generator backup panel is necessary to maintain the integrity of the grounding system and to prevent the flow of neutral current through unintended paths. When sizing a neutral conductor, one must consider the type of loads connected to the circuit. For example, lighting loads typically have a higher harmonic content than resistive loads, which can increase the current flowing through the neutral conductor. Similarly, electronic devices such as computers and televisions can also generate harmonic currents that contribute to the neutral load. The NEC provides specific guidelines for calculating the neutral load in these cases, taking into account the harmonic content of the loads. In addition to the type of loads connected to the circuit, the length of the circuit can also affect the sizing of the neutral conductor. Longer circuits have a higher impedance, which can cause voltage drop and increase the current flowing through the neutral conductor. Therefore, it may be necessary to increase the size of the neutral conductor for longer circuits to compensate for the increased impedance. When installing neutral conductors, it is important to ensure that they are properly connected to the grounding system. The NEC requires that the neutral conductor be grounded at the service entrance or at the source of a separately derived system such as a generator. This grounding connection provides a low impedance path for fault current to return to the source, which helps to ensure the proper operation of overcurrent protective devices. It is also important to ensure that the grounding electrode system is properly installed and maintained. The grounding electrode system consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes that are connected to the grounding conductor. The grounding electrode system provides a path for fault current to dissipate into the earth, which helps to prevent electric shock and equipment damage. When working with electrical systems, it is essential to follow all applicable safety precautions. Always energize the circuit before working on it, and use appropriate personal protective equipment such as gloves and safety glasses. If you are not familiar with electrical work, it is best to consult with a qualified electrician. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others. It is very important to understand how to read the amp probe correctly. An amp probe is an electrical test instrument that measures the amperage of a conductor without making direct contact with it. It works by sensing the magnetic field around the conductor, which is proportional to the current flowing through it. Amp probes are commonly used in electrical troubleshooting and maintenance to measure the current in circuits, identify overloads, and detect ground faults. There are two main types of amp probes: clamp-on amp probes and flexible amp probes. Clamp-on amp probes have a hinge jaw that can be opened and closed around the conductor to be measured. Flexible amp probes, also known as Rogowski coils, have a flexible coil that can be wrapped around the conductor. Clamp-on amp probes are generally more accurate and easier to use than flexible amp probes, but flexible amp probes can be used to measure conductors in tight spaces where a clamp-on amp probe would not fit. To use an amp probe, first select the appropriate range on the meter. If you are unsure of the amperage, start with the highest range and then decrease it until you get a reading. Open the jaws of the clamp-on amp probe or wrap the flexible coil around the conductor to be measured. Make sure that the conductor is centered in the jaws of the clamp-on amp probe or that the flexible coil is evenly wrapped around the conductor. Read the amperage on the meter. The meter will display the amperage in amps. It is important to note that amp probes only measure alternating current, AC. They cannot be used to measure direct current, DC. When using an amp probe, it is important to follow all safety precautions. Make sure that the circuit is de-energized before connecting the amp probe. Wear appropriate personal protective equipment, such as gloves and safety glasses. Do not use an amp probe in wet or damp environments. Inspect the amp probe before each use to make sure that it is in good condition. Do not use an amp probe if it is damaged. If you are not comfortable using an amp probe, consult with a qualified electrician. Understanding the limitations of amp probes is also very important. Amp probes are not as accurate as direct measurement methods, such as using a multimeter. The accuracy of an amp probe can be affected by several factors, including the position of the conductor in the jaws of the clamp-on amp probe, the presence of other conductors nearby, and the frequency of the current being measured. Amp probes are also not able to measure very low currents accurately. Therefore, it is important to use an amp probe with the appropriate range for the current being measured. When using an amp probe, it is important to take multiple readings and to average them together. This will help to improve the accuracy of the measurement. It is also important to be aware of the potential for errors when using an amp probe and to take steps to minimize those errors. When working with electrical systems, it is important to have a thorough understanding of the National Electrical Code (NEC). The NEC is a set of standards for the safe installation of electrical wiring and equipment. It is updated every 3 years by the National Fire Protection Association (NFPA). The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is essential for electricians, electrical contractors, and other electrical professionals to be familiar with the NEC. The NEC is not a law, but it is often adopted by state and local governments as part of their building codes. This means that compliance with the NEC is legally required in many jurisdictions. The NEC is also used by insurance companies and other organizations to assess the safety of electrical installations. There are several resources available to help people learn about the NEC. The NFPA offers a variety of training courses and publications on the NEC. There are also many online resources available, such as websites, forums, and blogs. It is important to stay up to date on the latest changes to the NEC, as the code is updated every 3 years. In addition to the NEC, there are other standards and regulations that may apply to electrical installations. These include standards from organizations such as the Institute of Electrical and Electronics Engineers (IEE) and the American National Standards Institute (ANSI). It is important to be aware of all applicable standards and regulations when working with electrical systems. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others. Always energize the circuit before working on it, and use appropriate personal protective equipment such as gloves and safety glasses. If you are not familiar with electrical work, it is best to consult with a qualified electrician.